Hi everyone, welcome back to ChemHelp ASAP. Today we are going to discuss enthalpy of solution. Let's jump right in. So enthalpy of solution is very simply a salt dissolving in water. Now, depending on what salt, this can be an exothermic process like potassium fluoride, or it can be an endothermic process like sodium chloride. Let's talk about the steps required to form a solution. So step one, we need to break the ionic bond between the cation and the anion. Now, this is actually the lattice energy of the salt. It's always going to be an endothermic process. So in general, you're going to have a metal and very often a halide or a polyatomic ion, and you're going to take that into the metal cation and the anion. So for our two salts that we're going to discuss, potassium fluoride and sodium chloride, their two reactions look like this. So again, I am breaking apart the cation and the anion, and I'm also sending them into the gas phase. Again, this is called lattice energy. Step two, we need to work on the solvent. So specifically, we need to create more space between the solvent molecules. In order to create more space between the solvent molecules, we actually need to weaken those intermolecular forces between the solvent molecules. Now, because we are weakening those forces, we're pulling those solvent molecules farther apart. This is going to be an endothermic process again. This is going to require energy. So very often our solvent is water, so let's see what happens when we have to pull water apart. So water molecules, of course, like to pack pretty tightly. This is a polar solvent, and what we want to do is we want to space them apart like this. So we want to make space for these ions in between the water molecules. We have one more step to form a solution. That is step 3 right here, and we are going to solvate or create spheres of solvation for these ions. Now, when we're talking about aqueous solutions or solutions in water, we call these spheres of hydration. Now, what this solvation or hydration is going to do is it's going to bring together the attractive forces. So it's going to bring positive and negative together. And this is going to be an exothermic process. So this is going to take energy from the system and release it into the surroundings. So for our anions, again, if we're talking about water as a solvent, you're going to orient the hydrogens towards the anions because those have the partial positive charge. For your cations, the opposite is true. The oxygen ends of the water are going to come up next to that positively charged cation because, of course, the oxygens have a partial negative charge. Now, these solvation processes do actually form three-dimensional spheres. I have only shown them as circles here, but they will entirely encompass both the anion and the cation. Again, they want to maximize those attractive forces between positive and negative. Now, we can actually calculate what the enthalpy of solution is for different salts. I have already told you that potassium fluoride is exothermic and sodium chloride is endothermic, but how do I know that? Well, you do a calculation. So let's see what this calculation looks like. Let's first take a look at sodium chloride. So I am plotting here the energy of all of these steps of solvation. So we start with our sodium chloride. It's just a solid. Remember, the first step is to create our ions. This is our lattice energy. So here I have shown my delta H of the lattice energy, and now I have two ions. Then we have what's called the hydration step. This is a combination of spreading apart the solvent molecules and also creating those spheres of hydration. So for sodium chloride, here is your hydration. Again, an exothermic process, and we have now formed our solvated cation and anion. So to calculate our enthalpy of solution, we're going to take the difference between the energy of step 1 and the energy of step 2, and this is our delta H of solution. So if we look at actual numbers for this process, our delta H of solution, again, is our lattice energy plus our hydration energy. And for sodium chloride, your lattice energy is 778 kilojoules per mole, and your hydration energy is negative 774 kilojoules per mole. Adding these together, I get 4 kilojoules per mole. Notice it is a positive number. This is an endothermic process. Now, it's not enough that when you dissolve salt in water, you can actually maybe feel that it's getting colder because it's only 4 kilojoules per mole, but it is an endothermic process. Let's contrast that with the enthalpy of solution for potassium fluoride. Okay, so here is, again, your graph for your enthalpy solution for potassium fluoride. We start with our potassium fluoride as a solid. Our lattice energy gives us our ions here. Again, a very endothermic process. Then our next step, of course, is to hydrate those 2 ions. So our delta H of hydration takes us all the way down here, and of course we get aqueous potassium and fluoride ions. The difference between where we started and where we ended is our delta H of solution. You can already see the difference between these 2 charts. They have the same steps, but of course, the magnitude of the lattice energy and the hydration energy are different, which leads to different signs for delta H of solution. So let me show you again those numbers for the delta H of solution for potassium fluoride. Again, we're just going to add our lattice energy and our hydration energy. So for potassium fluoride, our lattice energy is 808 kilojoules per mole, and our hydration energy is negative 826 kilojoules per mole. This gives us an enthalpy of solution of negative 18 kilojoules per mole. The enthalpy of solution for potassium fluoride is exothermic because you get a negative value here. So it's all in comparing the magnitude or the number of the lattice energy versus the energy of hydration. When your energy of hydration is larger than your lattice energy, that's going to give you an exothermic enthalpy of solution. If your hydration is not as large as your lattice energy, then that's going to give you a positive value for your delta H of solution, and again, an endothermic process. This is just yet another example where being careful with your signs is really important. I hope you found this video helpful, and thanks so much for watching.